Hello and welcome. In this video, we're going to talk about perhaps the most powerful machine learning algorithm that's known as support vector machines. If you follow this video along, you'd realize why this algorithm is so popular. What makes it so strong? Support vector machines have been the preferred choice for solving very difficult machine learning problems for several years. So we'll deep dive into support vector machines in this video. And if you follow our videos, you'd realize that we cover a different depth to all the topics that we introduce to you. This video would provide you complete clarity on how support vector machines work and why they are different from the rest of the algorithms. Let's get started. So let's say we are talking about a classification task where we have these two classes, the red and the blues. And we have to find out a way to segregate these classes, so that if we get a new observation, let's say somewhere here, we are confidently able to say that this is going to be red. If we get a new observation somewhere here, we are confidently able to say that it should be tagged as blue. Now, to us, it seems like common sense because we can imagine drawing a line anywhere here in between, and we'll say that that is a good segregator. But is that such an easy task for a machine to do? Well, obviously not. So how would a machine approach solving this problem? A machine would try to draw a line like this. Is this a good line? Well, it is doing segregation right now, but if you see, this is kind of very close to some of the edge cases. So if you get a new observation, which is what we get in the test data, we may not be able to maintain this line as a segregator. We may begin to commit errors. So we don't want to be making such decisions which are less generalizable. The moment there is a change, they begin to generate errors. We don't want to be doing that. So this is not a good line. Then what can we do? Can we look at this line? Well, again, this line is doing the segregation right now, but it is not, again, very generalizable. Why? Because this line is again touching this point almost here. It is a good classifier as long as we are talking about training a model. But the moment we get new observations, which are slightly different, this line would also not serve the purpose. Then can we look at this line? Okay, this line seems to be somewhat nicely separated from all the points. It's kind of taking a middle path. It's doing the segregation right now pretty well. The earlier two lines were also doing that. But this black line, if you see here, is also keeping something that we call as a margin. So it's not prone to errors due to lack of generalization. When you show new records, it will still be able to maintain some margin and classify them correctly. So let's get the margin here. This is what we meant. It is leaving this gray band as a margin instead of just touching these points on either side or both the sides. It's making its decision somewhat wisely. So these bands on either side would be called margins. We can denote it by M. It's some distance that it has kept as a buffer. And these points that are touching the margin, not the line or the plane, these points that are touching the margin are called the support vectors because our decision relies on these points. Now, for a classic machine learning algorithm, what happens is if you get a point here, you'll be very confident that this is going to be blue. Or if you get a point here, you'll be very confident that this is going to be red. So most of the machine learning algorithms are good at making decisions in these dense regions where there is a lesser chance of making a mistake. But it turns out that support vector machines make the decision based on support vectors. And interestingly, it turns out that they only rely on these support vectors for making decisions. So even if I remove all the points, as you can see now, the decision wouldn't change. Support vector machines only rely on these points to make this decision of classification. That this is how a line or a plane should be placed to segregate the classes. Which means if we even had outliers along with the points earlier, it would not influence the decision of a support vector machine. Why? Because support vector machines, as we saw, are relying only on the support vectors for making decisions. So even if your data contains outliers, while most of the other algorithms would be affected by the presence of outliers, support vector machines in terms of decision making would not be affected by the outliers to that extent. Relatively robust to the presence of outliers, you can say. Now let's understand the line or the plane, which is separating these two classes a little better. We'll start with an example of a line and then we'll generalize it to a plane because the limitation is that we can only visualize the things in 2 dimensions comfortably. So let's focus on this line right now. And let's say these are the points that this line is helping us segregate with a margin M. What is the equation of a line? The typical equation of a line is ax plus by plus c is equal to 0, where a and b are called coefficients. Or in other words, we can represent it like this, where we are saying our variables are x1 and x2, and their coefficients are W1 and W2 respectively. W0 here represents the intercept or the constant term. Just another way to write the same equation of a line. Well, how does it look like when it becomes a plane? It's a summation of values ranging from 1 to n of wi xi. So you will write it as w1 x1 plus w2 x2 plus w3 x3, so on and so forth, till wn xn plus w0. You can see this is just an extension of the equation of a line. This is called a plane. Because while solving machine learning problems, we will mostly not be dealing with one or two features alone. We should have an understanding of the planes a little better. Because any data would commonly have several columns, 15, 20, 50 columns maybe, right? So we should understand how would the scenario be in case of a multi-dimensional data. We cannot visualize that, but we can imagine plane would act as a segregator for classification tasks in those scenarios. And when would the plane be a good classifier? Let's understand this a little better. So we've taken the picture to the left so that we can write our equations here. So you can imagine there are 2 points above the plane and 2 points below the plane. These are PQ and RS respectively. For points PQ, which are above the plane, when I put them to this equation, we should get a positive value. Why? Because if I take a point on the plane, it should satisfy this equation, which means if I take a point somewhere on the plane, it should give me a 0 as an output. Whereas if I take points above this plane, it should generate a positive value when those points are put to the equation of the plane. Similarly, when I take a point below the plane, it should generate a negative value. So what we are saying is that the plane is able to separate the two classes. If I take a point which is above the plane and I put it to the equation of plane, I get a positive value. If I take a point below the plane and I put it to the equation of the plane, it should generate a negative value. Let's say now we introduce the classes. So let's say a class label above the plane is 1 and the class label below the plane is -1. Now let's try to understand what are the conditions that we should satisfy. So if we take a product of this label, which is 1, and multiply it with the equation of the plane. For points above the plane, you can imagine this is a positive quantity, like for points P and Q. And this L is also something which is +1. So if we multiply this, we should get a value greater than or equal to M. Notice, if this would have not been a classifier which uses a margin, we would have written this should be greater than or equal to 0. But since we are respecting the margins and we choose our classifier based on the margin, we are saying the product of these two quantities, which is this class and a positive value for the plane, should be greater than or equal to M, which is the margin. And let's say we choose a point below the plane. So you can imagine this quantity here then would be a negative quantity. But you are going to multiply it with the label L, which is a -1. So again, a -1 multiplied with a negative quantity, you will again get something positive. In that case, again, we want this to be greater than or equal to M. This is a very important condition you should remember, because every algorithm that you would study would always work on some logic and would satisfy some conditions. These are the critical conditions for support vector machines to work. And in addition, there is another condition that's required to be satisfied for support vector machines is that the sum of squared coefficients should add up to 1. This is a part of standardization. Because we are working on margins and distances, it is nice to have the coefficients on comparable scales. And that's why we are saying the sum of squared coefficients should add up to 1. Now, try to increase the width of this margin a little further and try to understand another concept. So far, we've been talking about the hard margin classifiers, which means this is not willing to tolerate any error. It nicely segregates the two classes and it does it accurately. But there could be points which fall within the margins, like these. For example, the point T is now lying within the margin width. Point U is lying within the margin width. And in such cases, we use something that's known as the soft margin classifier. We are more practical here. We are saying, while we will try to maintain the margin, but there could be cases, there are a few points which lie within the margin. And even further, there could be points which are misclassified, like points V and W. If you see, we would imagine all the reds being on one side, but this red point here went to the other side of the margin. Likewise, this point W, we anticipated it to be here above the plane, but it went to the opposite side. So to deal with such scenarios and for more practical reasons, we use soft margin classifiers. And this requires us to introduce the idea of a slack variable. What is that? So remember, this equation is something that we saw earlier as well. The product of the label multiplied by the plane. And we were saying that this is to be greater than or equal to M earlier. But now, since we are becoming more practical, we are saying we may not be able to maintain it strictly to M. because there may be some amount of slack. So this epsilon I that you see here represents the slack for an observation I. If this is 0, you can imagine we will be doing a hard margin classifier. But if this value is between 0 and 1, it means that we are talking about these points T and U. So if the value of epsilon is between 0 and 1, then we are talking about the points which lie within the margins. They've not violated the margins, but they are within that band. However, for the points which are misclassified, which are classified onto the opposite side, this value would be greater than 1. Theoretically, epsilon can even take values up to infinity, but broadly speaking, for the points within the margins, this will be between 0 and 1. For the points which are completely misclassified, placed on the opposite side, this will be greater than 1, you can imagine. The farther it is from the margins, the greater this value of epsilon would be. Notice that we do not directly control the value of epsilon, so we cannot pass it like a hyperparameter. This is to be learned by the algorithm. However, what we can control is the total budget on these errors or slacks. We can say that the sum of all these epsilon i's or the slack variables should be less than a certain cost. And there is a hyperparameter available in scikit-learn to tune this. Now let's understand the kind of loss that the support vector machines follow. So we know the equation of a plane, we know the actual label. There is a concept of hinge loss that we talk about here, which is the maximum of 0 to 1 minus L multiplied by Y, label multiplied by the value of the plane. If this Y here represents the predicted output and L represents the actual label. So generally, if for an actual label 1, the predicted output is greater than 1, then you don't have any loss. So you can imagine if you're predicting a value greater than 1, the product of these two quantities, 1, which is the actual label, multiplied by a value greater than 1, would exceed this 1. So this would become a negative quantity. So max of 0 and a negative quantity would be 0. There is no loss. Similarly, for a class label -1, if we predict a value y, which is less than -1. So imagine this is negative and you multiply it with the negative quantity. And overall, we already have a negative sign outside. So this again would become a negative quantity. And between 0 and this negative quantity, 0 would be the loss. So to summarize, if the actual class label is 1 and our prediction is a value which is greater than or equal to 1, we will not have a loss. Similarly, for an actual label -1, if our prediction is anything which is less than or equal to -1, we will not have a loss. And for the other predicted values of y, we will see a linear loss like these. So this is actually the loss function that works under the support vector machines. So support vector machines were originally introduced in the 1960s. But a major breakthrough came to support vector machines in the year 1992. And that was when they started using non-linear decision boundaries by relying on a very smart trick known as the kernel trick. We'll talk about that now. So let's say our data is not linearly separable. So far, we talked about this kind of scenario where we could linearly separate the data using a line or a plane. But what if the task at hand requires us to segregate these two classes? Now you can imagine drawing any one line would not help you segregate these two classes. Line is not a solution to this problem. We'll have to think of it beyond a line. What could be a solution? Looks like an ellipse could be a solution. So maybe we can draw a decision boundary which is non-linear, and this would help us segregate these two classes. But the problem is, this is a two-dimensional data. We could eyeball it and figure out that it can be solved using an elliptical shape. In a multi-dimensional data set, and that's what we mostly work on, it is not going to be so easy to visualize it and imagine that you can draw a circle or an ellipse or a sphere. It's not going to be so easy. So is there a smart way that we can work on it and still find a solution without having the data visualized? Let's understand that. So what is the equation of an ellipse? From your high school geometry, you would remember it's generally written as x squared by a squared plus y squared by b squared is equal to 1. A circle is a particular case of ellipse when a and b are equal. What if we carry out a small transformation? We say we would want to transform the axes in such a way that x squared is called x prime and y squared is called y prime. So in the same equation above, if we replace the x squared with x prime and y squared by y prime, how would that look like? Now, if you realize this is the equation of a line in terms of x prime and y prime, where you can say the coefficient of x prime is 1 over a squared, coefficient of y prime is 1 over b squared. And you have an intercept on the opposite side, which is 1. If we carry out this transformation, what we get is something like this. The same data that you saw in a circular elliptical form turns out to be something what you see on the right. And if this is how we can transform the data, then we know that we can still use a linear separator like this. So now the problem that we were not able to solve using a linear separator can be solved using a linear separator by transforming the data. When I say transforming the data, this is not an explicit transformation. This is known as the kernel trick, which is an implicit transformation, which means you're not adding new features to your data. It's only for the purpose of decision making, you're projecting data to a higher dimensional space and using a linear separator. This is a very important point. Generating more features would further increase the complexity of the algorithm. So this is not same as the polynomial feature transformation or polynomial regression kind of problem. This is done implicitly. We're still using a linear separator for making decisions, but you can imagine this is doing its work implicitly. This is just an example to demonstrate how choosing a transformation on the data enables you to still use the linear separator and solve the problem. Let's understand this a little better with the help of some interactive plots. So scikit-learn provides us with a couple of kernel choices. Like I said, we may not be able to proactively visualize the data in a multi-dimensional scenario and imagine that what kernel works for our data, but we'll have to experiment with these kernels. So let's say our data is like this. We have two classes, blues and reds. Right now, when we look at it, we can imagine probably a linear kernel would also do the job here. We can draw a line and segregate the two classes. And we can, of course, argue about the width of the margins and things like that, but that's a separate case. What if this kernel was to be changed? And how does changing the kernel affect the decision boundaries is what we want to understand here. So let's say I choose the kernel to something that's a polynomial kernel. Polynomial kernel would have generated polynomial features, derived features out of given features, and then it'll try to do the segregation. Let's see what happens. So you can see the decision boundary, which was a straight line earlier, got a little more twisted, and it's using a polynomial kernel to do a classification task. But the most popular kernel in case of complex arrangements of data would be an RBF kernel or radial basis function kernel. Look at it to understand how does it work. So you can see this is drawing very different decision boundaries. It's drawing this plateau-like shapes where it's kind of segregating the classes using these decision boundaries. You can call it an enclosed region to do this kind of segregation. And here you might be wondering, did we actually need this complex a decision boundary? No, probably for this case, you did not need this complex a decision boundary because your data is linearly separable. But like I said, you would not always know by visually inspecting it that your data is linearly separable or not. And that is where the importance of trying different kernels comes into picture. These are some of the hyperparameters that we can tune. So the C here that you get is inverse of the total cost of slack. We will emphasize more on this when we learn how to apply these models. And this gamma is another hyperparameter which talks about complexity of the decision boundaries. In general, high value of C and high value of gamma would lead to overfitting. And low value of C and low value of gamma would not even do the sufficient fit. So we have to often tune these hyperparameters to get better results. You'll see if I change the value of C, the outcome would change a little bit. Notice this hyperparameter gamma is not applicable for linear kernels. It would not have any effect on that, but it would affect the outcome of the other kernels. You can see the value of C is changing the boundaries a little bit. Let's take an example of a scenario where our data is not linearly separable. Probably then you'll be able to appreciate the use of the RBF kernel. So let's look at this data. And you can imagine this is a scenario where the red points are surrounded by these blue points all around. Of course, a line here would not be able to nicely segregate. If you choose this line and say all of these are supposed to be blues, you're going to make a lot of mistakes here. Similarly, the other way. So in this case, if we would have chosen an RBF kernel, what would have happened? See how nicely the RBF kernel is able to segregate the reds from the blues because it's taking this kind of a shape of a plateau. So choice of kernel is a very important input depending on the kind of data that we have. Now, support vector machines are not only used for classification tasks, these are also used for regression tasks. So in this picture, if you see, we've kind of negated the influence of color. We are not saying it's any longer between the reds and the blues. We are saying this is just one color and we want to represent these points. So how do we use support vector machine as a regressor to represent these points? The same concept of margins works here as well. What we are looking at now, how many points fall within the margins? So we have these margins M on both the sides of this hyperplane or a line, you can say. We are interested in seeing the points within the margins are nicely represented by this plane. But the points outside the margin would be adding on to some error. And again, the loss function in this case would vary depending on how far the point is misclassified from the margins. So the farther it is, the greater the error contributed by that point is. So remember, support vector machines are used both as classifiers and regressors, and these are really powerful algorithms. Hope you got some intuitive understanding and more clarity on the common terms associated with support vector machines. You will get further more clarity when we apply it in practical sense using some real data.